meeting. I'll be talking about the gas around the SMC and LMC. So we're going to have two keynote talks, this one and the one from Claire Murray next. And the way we decided to split this is I'll be talking about the gas around the cloud, so the CGM of the LMC and SMC. Claire will tell you about the ISM inside the clouds. I also want to start by thanking the many collaborators that I've worked with on this area of science over the last 10 or 20 years. If their names are in yellow, that means they're here at the meeting, either in person or online. And all this would not be possible without these collaborators. So we don't need much motivation for studying the gas in the clouds with this audience, but I still want to make a couple of points over why we can learn so much from studying this gas. We can obviously learn about the LMC and SMC themselves by studying the gas around them, because the gas tells the history of their past dynamical interactions and the processes that caused this gas to be released. So this is a way of learning about the clouds. It's also a way of learning about the Milky Way system, because the fate of a lot of this gas that we see around the LMC and SMC is to ultimately fall onto the Milky Way, certainly into the halo. Much of this is being incorporated into the Milky Way halo. Eventually, some of this gas will come into the disk of the galaxy. So this gas that we are essentially taking from our neighbors in the satellite galaxies, a lot of it will end up in the Milky Way. So this has big implications for future star formation rates in our galaxy, and that's another reason of interest. And there's a third reason I think we also just learn a lot from this system, and that's about the CGM in general. So there's one thing we know about all this gas, and I'm going to show you the evidence for this as we go through the talk. But we know that this stream and leading arm, this strip gas used to live in the LMC and SMC. And this seems pretty accepted by the communities, that we're seeing gas that came from the LMC and SMC. Now, why is that important? People study the CGM at all redshifts. And generally, when you see gas around galaxies, you don't know where it came from. You have ideas. It could be inflow, it could be outflow, it could be strips, gas from satellites, but you don't usually know for sure. You can't pinpoint where gas came from in the way we can with this system. So it gives us a really great example of tracing the history and tracing the narrative of the gas, because we know where it came from. And in general, even for clouds around the Milky Way, our own galaxy, we can't do that, because there's so much various models, so many models for explaining it. But with the LMC SMC, we think we have a good picture of that. I'm going to start with a brief word on history, and then I'll get into the observations and what we know. And I wanted to talk about when the stream was discovered and how it was named, because this is very relevant to one of the themes of the meeting, of the naming of the clouds. So back in the 1960s, radio astronomers started seeing a bunch of H1 in the southern hemisphere. And you can just look at the titles of papers to see this. You don't even need to look at the figures, right? What were they saying? They were saying neutral hydrogen near the galactic poles, an unusual high velocity hydrogen feature, a systematic search for hydrogen. So people realized there was H1 in the south, a lot of neutral hydrogen out there. Now in the 70s, this name came along from this very foundational paper from Matthewson and collaborators, where the term the Magellanic Stream first appears. And so they put together all these different pieces of H1 and realized this is one coherent filament, and it connects to the clouds. And because it connects to the clouds, it was given the term the Magellanic Stream. So why am I mentioning that? Because this was also presented at an IAU meeting, by the way, back then. So they went through the IAU, as is suggested for the recent naming debate. But naming something is kind of remarkably easy, right? The authors decided this was a term that made sense because the stream connects to the clouds, so they used the term in their abstract. Of course, renaming something is much more complex and controversial. But if you look at, this is where the term first appears, right? It's because the author said, we're going to call it that, right? And this term has been used since then. So that's where it came from in the sense of the stream, and it's been used in the literature since. It's not gone unnoticed that there's another parallel here. Magellan is famous for many reasons, including the fact that he captained the first circumnavigation of the Earth. That was a major scientific accomplishment, and it also had a lot of implications, both positive and negative. But it was a major feat to travel around the Earth and measure the circumference of the Earth with that precision. So there is a nod here to the fact that this was a navigator and an explorer, and the stream circumnavigates the galaxy. That was an intentional choice of words in this annual review article a few years ago. I'm certainly aware this is a complex subject, but this is a stream that is named after a navigator and an explorer. And so there is another element of that I think is probably worth considering. But that's enough of that. Let me show you the data. Back then, 50 years ago, this is the Matthewson data on the H1 in the Magellanic System. You could already see the stream and some of the leading arm and some of the bridge, these structures that we still study today. So even with what by today's standards were not very sensitive radio data, it was discovered and a lot of progress was made from this. Since then, there's been many all-sky H1 surveys. There's been the high-pass survey from the Parkes telescope and more recently other surveys. And this abundance of H1 data has led to a lot of work, a lot of studies of the structure and the composition. So this is work from Mary Putman in '98, where the leading arm was shown that it connects to the LMC, right? So you could see earlier on that there was gas near the LMC, but you need to show that it's physically connected. And the way that this is done is with kinematics. You can look at the velocities of the gas and you can see, and this is what's done in the Putman paper, that if you take a channel map, this is at a certain velocity, 320 kilometers per second, this gas is tracing back up through the leading arm towards the edge of the LMC. So you need to look at the kinematics to study this. This has been shown in more recent data. This is the famous Nidover map of the system. We've seen this week showing lab data and other data. And more recently, there's the gas survey from McClure-Griffiths et al. That's been used for this rendition of the Magellanic System from Scott Lucchini's work. So we've been able to benefit from these surveys that have been publicly available and that have shown this structure in the H1. Okay, so let's talk about some properties of the gas. One that we know reasonably well is metallicity. There's plenty that we don't know very well, but I'm going to start with metallicity because we have a pretty good picture of this. So I'm going to show you some ultraviolet measurements of the abundances in the system. These come from the COS spectrograph on Hubble. Now, before COS was installed, this is the UV spectrograph on HST, we had 3 measurements of the gas phase abundances from different groups. And they were in different parts of the system. And these are solid measurements. We don't have any of them, right? So in the leading arm, there's a measurement from Lim and Liu, and they found a sulfur abundance of minus 0.6 in the log. That's about a quarter solar. There's a measurement here near the LMC from Brad Gibson, and they found about a half solar. And we found a direction at the far end of the stream where we could do an abundance measurement, and we found 1/10 solar. So the point is it's different in all 3 places, right? So back then we didn't really understand what the narrative was there. And by the way these observations are made is by combining H1 observations from radio to get the hydrogen column with UV observations to get the metals. And then the metallicity is essentially a ratio of the metal column to the hydrogen column. We use lines like oxygen and sulfur because they have small corrections for dust and ionization, and so they're some of the more reliable chemical abundances that we can do in the UV. So these are oxygen and sulfur abundances. Now, after COS, that was put on in 2009, we got a lot more measurements. I think as of now, I've counted up to 11 measurements of the abundances along individual sightlines through the stream published by different authors. So we have a better picture. And what we see is most of them are around 1/10 solar. Anything in yellow there is near 1/10 solar for a metal abundance. But there are a couple of higher metallicity measurements near the LMC and in the leading arm. So there's still some places where the gas is more metal enriched. And so there's still some variation. And I think the key to figuring this out and what it means is to look at the filaments. So go back to the H1 data. So one of the key properties of the stream is its filamentary. It contains these long threads of gas that are coherent. You can see them in this early high-pass data from Putman, very clean filaments. And what David Nidover showed in his 2008 work is that the 2 filaments have different kinematics. One traces to the LMC, that's shown in red. But if you take a different velocity filter, you pick out a different velocity of gas, that one traces to the edge of the SMC. So we're seeing gas with kinematics tracing back to both clouds. What's really neat is if you then go back to the chemical abundances, you find that you get the same story. The 2 filaments have different abundances. So if we find sightlines behind the LMC filament, for example, we have this quasar here versus ferrol 9, we do the same game, we measure the abundance of sulfur, that comes out at half solar. Here's the data below from which that measurement is derived. In the other filament, it's down at 0.1 solar. And that's the filament that connects to the edge of the SMC. So there's a clear difference in abundance between the 2 filaments, telling us, like we saw from the kinematics, that the stream contains gas from both galaxies. There's an LMC contribution and an SMC contribution, right? Both are sourcing the material. That's really why this is important. In terms of which gives more, probably the SMC by mass. And that's not surprising if you look at the models, because the SMC is a lower mass galaxy. It's harder to hold on to gas with a shallower potential well. So the SMC is donating more of this gas, but it is coming from both galaxies. Okay, next I want to talk about ionization. Now this is another subject that we can use the UV data to learn about. So we've been measuring these quasars behind the stream for many years. In 2014, we measured this sample of about 70. So these are sightlines where we can point Hubble at a background target. Many of them were archival targets, so the data was there, but we took some more data to finish the sample you see here. So we can measure the abundances in different parts of the stream and look at the ionization. So how do we measure how much ionized gas is there? It's complicated, and you have to use cloudy ionization modeling or other models, but the kind of, in a nutshell, you're measuring lines of different ionization state. So we look at silicon 3 and silicon 2, which are two UV lines that we cover with COS. The ratio of those two lines, that ion ratio, is an indicator of the ionization level in the gas. So you can model that along each sight line. I mean, I've just shown one there as an example. You measure the absorption, and then you run a model and you derive how much ionized gas is there. Then you can, if you have an idea of the cross section, then you can turn your column density along one sight line into a total mass. And the cross section in ionized gas is big because we're seeing this gas even beyond the H1 contours, right? So the pink emission here is the H1. The yellow stars are sight lines where we see absorption in the UV at the same velocity, but it's off the edge, right? The implication is there's ionized gas at those velocities that's associated with this stream in some way, but it goes further than the H1, right? The H1 is giving you a subset of all the gas. The ionized gas is more extended, so it has a bigger cross section. So how much mass is there? If you integrate over the area of this absorption on the sky, you can compare how much H1 mass there is and how much H2 there is. And we get a number of about 1 to 2 billion solar masses of ionized gas from these UV measurements. For comparison, the total H1 in this system, this is not in the clouds, by the way, this is the gas outside, right? The stream and the leading arm and the bridge. That adds up to about 4 times 10 to the 8 solar masses. So that would suggest there's more ionized gas than neutral gas by mass. Now, if you look at this in H alpha, which is a completely different method, and this is what Kat Barger and collaborators have done, you also find over 1 billion masses of ionized, over 1 billion solar masses of ionized gas. So that number is coming both from the UV studies and the H alpha. That's good because they're very independent. They're not relying on each other. So there's a lot of ionized gas there. That's really the takeaway, whether you measure it in UV or H alpha. Now, how much does it represent? I think it's useful to turn that into a mass flow rate, right? A mass is a mass of gas. If you know the infall time from the velocity of the gas, you can get a sense of the inflow rate, the mass flux in the ionized gas. And the 1 billion solar masses of ionized gas represents an inflow rate of a few solar masses a year towards the Milky Way. Now, not all of that has to come in necessarily. It has to survive through the halo, and some may be ionized, some may be stripped. There's various things that could happen, but there's still that much mass of gas coming in. And for comparison, that's more than all the other HVCs in the Milky Way, which are about half a solar mass a year. And it's of the same order, within a factor of 2 or so, of the Milky Way star formation rate. So that's why we're interested in the galactic context, right? Is there's enough fuel here to change the star formation rate in the future if the gas gets in. And whether it does is an open question, of course, but there's certainly material that may be of significance to the baryon budget of our own galaxy. Now, you can also look at this in H alpha, as I mentioned, and here's a plot showing the H alpha intensity in the stream along the longitude, along the stream longitude from Barger et al. And there's a lot of observations on here with the different circles, and then there's various models for how bright we expect the H alpha to be from the stream. So one of the points to make here is I want you to look at this horizontal line here, this EGB extragalactic background. So if you say, let me model the stream with ionization from the UV background, that's how much H alpha you should get if it was photoionized from the UV background. Not much. In these units, that's about 20 millirayleigh. Not much. You'll see every observation is much higher than that. So the UV background is not enough to explain how bright the stream is in H alpha. You need something else. Could it be Milky Way radiation that's escaping from the galaxy? Those are the different lines that are shown here with different colors. Then the question is, how far is the stream? What's the distance? Because the closer the stream is to the galaxy, the brighter it will be in H alpha. And that's not well constrained observationally. We don't know that distance. So you can see the 4 different colors here. If it was as close as 50 kpc, which is the purple line, you get closer to explaining a lot of the observations, but not all of them. And there are some points that have been noticed which are way brighter than that even. There's, especially near the South Pole, there's some really bright H alpha coming from the stream, and people are trying to figure where that's coming from. So the point is, you may need another source of ionization. The UV background definitely isn't enough. The Milky Way radiation may be enough, but even then, that's not explaining anything. So there are some other models out there for what could be ionizing the stream. One model that is being published recently is led by Joss Bland-Hawthorne, and this idea is a Seyfert flare. So we know there's a supermassive black hole in the center of the Milky Way. There's some evidence that a few million years there was an outburst. We know there are Fermi bubbles and other structures near the galactic center that are age dated to be a few million years old. So something happened and that event could have released a lot of radiation. And the point is that the stream, just by where it happens to be, passes through like above the minor axis of the Milky Way. So if there is a bright radiation that comes out from the Milky Way, the stream is going to feel it just based on where it is. Whereas the leading arm is kind of sheltered because it's off to the side. So the idea in this model is that maybe there was a flash of radiation that came out from the center and ionized the stream. Now, how can we test that? Or how can we look for evidence of that? We can look at ion ratios. So this is one showing the carbon-4 to carbon-2 ratio along the stream. And there is a lot of scatter, but there's some evidence that this ratio changes with longitude. And it changes in a way that the ratio is higher near the South Galactic Pole and lower in other places. But there's also just a lot of scatter there. So I don't think we can learn anything conclusive from this, but there is a region where the ratios are elevated near the South Pole. That's consistent with a flare, but this is not a smoking gun or any type of confirmation. It's consistent with it. Another thing we could do is we can look at the kinematics of the absorbers, because if the gas is photoionized, now we know what photoionized gas looks like in absorption because we can measure the profiles, we can look at the line widths, and we can see if they're consistent with a photoionization model. So we look in different states. This is showing ions of carbon-2 or silicon-2 or silicon-3, different ionization states, and we can look at how their kinematics compare. So what we find is that there is a different distribution in how the line widths look in the leading arm versus the stream. So if you look in the stream, the kinematics are very simple, right? The stream has quite simple kinematics. In all these different ion lines, you're seeing similar line widths, and the different ion states line up. So that's a kinematically simple, fairly undisturbed gas where all the different traces have similar kinematics. In the leading arm, we see a different picture where there's more evidence for multi-phase gas. We see broader lines in the high ions like silicon-4, narrower lines in the low ionization species. So there's a different distribution in the leading arm and in the stream. So this is consistent with an idea that the stream is predominantly a single phase medium. It doesn't by any means prove that there was a Seyfert flare. We can't go that far for sure, but we can say that these absorbers show the properties of photoionized gas, and the Seyfert flare is one model for doing it. So this is the model that we're still looking into. The open questions that still really need to be confirmed to help this is, firstly, what's the distance to the stream? If we know how far away it is, we have a much better handle on how bright it should be in H alpha, right? That's a key thing that needs to be measured. And we also need to consider, can you get H alpha from other ionization sources? If you have shocks, and that's been brought up at this meeting, is there maybe a bow shock? If that gave you H alpha, that's going to complicate this, and that needs to be accounted for. So there's certainly more work to be done on this idea. But it shows that the stream is another use of the stream, right? It's a Swiss Army knife, right? Here we're using it as a probe of the radiation field below the galactic center, right? It's in the right location to tell us something about that radiation field. Okay, so the last topic I want to touch on before the end here is about what else is there in the CGM of the LMC and SMC. I've covered the stream and the leading arm so far. That's partly because there's so much work that's been done on them, and they're They've been the focus for a long time. But the LMC very likely has a lot of other gas, just as diffuse CGM like any other galaxy. And this is something that people have started to look at more recently. One of the key motivations is this high mass for the LMC. We heard several talks about this already at this meeting. What that does to the Milky Way, what that does to the dynamics. I mean, it's a big galaxy, right? So we've heard all this amazing recent work on characterizing the mass of the LMC halo using different techniques and converging on a number above 10 to the 11, right? So this is not this little dwarf galaxy, right? This is a massive irregular that's causing impact on the Milky Way. And it matters for the CGM too, because a galaxy of that mass should have its own CGM, right? A galaxy of a mass over 10 to the 11 solar masses, first of all, you can just say, what's the virial temperature for that mass? Just real simple back of the envelope. If I have a halo mass of 10 to the 11, how hot should I expect the virial temperature should be? It comes out as a few 100,000 Kelvin. That's a warm, hot temperature. We can probe that in the UV. And so we expect some coronal gas, right? Warm, hot gas, just from that mass, okay? Now, virial temperature is a simplification, of course. If you look at a simulation of hot gas in a galaxy halo, you also see temperature 10 to the 5 warm, hot gas in that halo, right? So there's plenty of reasons you should expect CGM just from the mass alone. So there's a number of recent projects that we've been working on, and you're going to hear about these from these three authors later today. So I'm just going to very briefly mention this because you'll get the full story from the folks doing all the hard work on this. The first was some simulations that have been led by Scott Lucchini, who's looked at the formation of the Magellanic System and the stream if you put in this hot halo, right? So there's been a lot of careful dynamical work on the stream over the years. We heard a review from Gattina on this yesterday, showing the orbits and the inflow of the gas. Adding the corona is a new ingredient, and adding that ingredient can change the properties of the stream. And so Scott will tell us about some of that work. We've also have some observational evidence for this in the form of UV absorption lines, and DK, who's talking later today, will be talking about that. And that's this plot here where we see a profile of absorption in different ions. This is carbon-4, silicon-4, and oxygen-6, and we see that these depend on distance from the LMC. And then finally, Sapna Mishra is going to be talking about the cool gas in this halo, because like most CGMs, this is a multi-phase CGM. There is not just coronal gas. We're seeing a lot of cool gas, maybe with different kinematics, and that's telling us something about the structure of this. So stay tuned for these talks later today. And again, the point is that we know a fair amount about the stream and the leading arm, but there's also this rest of the gas, this diffuse CGM. And that's something that I think is a much more ongoing area where we're finally starting to see that the rest of that non-tidal gas, the regular CGM. So here's the picture of this corona, right? It's a diffuse warm hot CGM phase that may extend out to a few tens of kiloparsecs around the LMC. Exactly how far it extends, I would say we don't know yet. And there's model predictions that can be useful there, more observations that need to be made. But this is the idea, is that as the LMC and SMC are coming in with their satellite galaxies of their own that we heard about yesterday, they would also be coming in with gas. And that gas can affect their evolution and their interaction with the Milky Way, because this is also a protective layer of gas, right? So from the point of view of the LMC and SMC, if you're surrounded by a halo, it is harder for the Milky Way to strip your gas than if you do not have any halo around you. It plays a role in cocooning the clouds. And so we think this is an important ingredient to think about when we talk about models of this system and their evolution. So I'm going to end with that, put up my summary slides, and just point out that we have all this work that's characterized the stream and the leading arm, and we're also beginning to get a handle on the rest of the gas around the LMC, the more diffuse CGM. And thank you for coming in for the first talk, and I'll be happy to take questions.
Any early career folks?
Yifei Jun from CFA, and thank you for the talk. A question is about the gas mixture in the stream, and you see there are some LMC and SMC component on the stream. My question is why this gas is not still mixed with each other and generate a new metallicity? So does that mean it indicates the time when this kind of stream collide with each other?
Yes, great point. Gas metal mixing is a complex process, and I know there's a lot of simulation work that looks at that. We measure, when we look at metallicities in the stream, for example, what it looks like is we're kind of seeing the metallicity when that gas was stripped, almost like fossil metallicity, right? So we measure this 1/10 solar abundance in the stream. That's consistent with coming out of the SMC about 2.5 billion years ago, if you look at the models from Gattina's work, from Scott's work. So it does look like that's telling you about the time. So in other words, SMC today is enriched to about 20% solar when you study the abundances today. We're seeing a level of 10%, so it's below the current day metallicity. So we do interpret that as a sign that, yes, it came out in the past. And that, so you're seeing the metallicity as it was when it came out. Now, then the question is, why hasn't it mixed? That's a great question. And that depends on what are the mixing processes between the surrounding gas and like there's a hot halo gas. Then you need to look at, okay, what's the metallicity of that phase and how does it compare to the metallicity of the cool gas inside it? So it will depend on the properties of the surrounding gas. I don't think we really know them that well. For example, like what's the metallicity in this hot gas? That's not well constrained. And if you're going to mix metallicities, you can either dilute or you can enrich. I don't think we even know which way it goes. Is it getting more metal rich or less metal rich? But so it will depend on the properties of the gas it's mixing with. And I think for the LMC system, those aren't very well known.
Hi, Avery Kim from Columbia. Thank you for a great talk. I have a question about how to separate the high ion phase and low ion phase. And also, like, what would you expect the difference between like the corona gas and cool clouds in terms of characteristics?
Yes, thank you. How do we separate the high ion and the low ion? So we measure both separately. And we fit both sets of lines. You know, we do void component fitting and we do them separately. So the first thing we do is we don't tie high ions and low ions. We let the high ions be fit independently because they may have different kinematics. And often we see that, right? So that's, I guess, the first thing we do is we model our absorbers as basically having a low ion phase and a high ion phase, and they're not required to be tied. So when we do that, it looks like the high ion phase is higher temperature, lower density, but it's still around the same velocity as the low ions. So we model them separately. We also do ionization modeling. I talked a little bit about the cloudy modeling to see how much high ions you can create from photoionization. And what we found, and DK has done some work on this, is that you can't really explain the O6 and much of the carbon-4 with the photoionization models, because they're just too highly ionized. The photoionization models just don't produce enough column compared to what we see. So for those ions, we interpret them as collisionally ionized gas because the cloudy models have such a hard time producing the observed levels. So it is model dependent, and it does require doing that ionization modeling to see how you can create the high ions.
Here, still on this side. Maria Rosa from Potsdam, thank you. So the talk is great. I was wondering, so the ISM of the LMC and SMC is different, right? So the LMC has been much more efficient in using up its gas than the SMC, and that's why we see that most of the stream gas is probably from SMC, although there is a component from the other. So I was wondering, does this impact also what we expect to see in the CGM? If the LMC was so much more efficient, I mean, I hope I explained it right.
Yes, I think it will impact what we see in the CGM. I think what we can say so far is we do see gas with the LMC abundance signature in the stream. So there is that LMC filament. There is other gas in the other filament that comes from the SMC. So we are seeing gas from both galaxies.
Yeah.
How that's related to efficiency, I'm not sure. Maybe the next speaker will talk more about that.
No, more in mass, right? I mean, in mass, I have a feeling that the stream is mostly SMC gas.
Yes. Because, yes, and that could be simply because the LMC is more massive, has a deeper potential well.
Yeah.
So it's
Okay.
harder to strip the gas.
Okay.
But it does look like there is at least some LMC gas getting out. And then also if you have a powerful wind from the LMC, and we've got talks coming up on that, say from 30 Doradus, you can maybe release gas from the LMC through a wind as well. So I think that will definitely affect the gas in the CGM. Yeah.
Questions over here?
Thanks. Wonderful talk, Andy. I'm wondering about, like, now that you can trace the CGM, like the diffuse CGM around the clouds, can you say something about the origin? Like, is it like the hot corona, at formation time, or do you also see a component that comes from the outflows? Like in general, like not just from 30 Doradus, like local, but in general from the star formation that comes out of the galaxy.
Yes, great point. And we need to do that. I think at this point, we're at the phase of just detecting the diffuse CGM and looking at its radial profile. That's certainly something we'd like to do, is then deriving abundances. And I would just say quickly, because if it was a primordial CGM, if it just came in with the LMC, it actually shouldn't contain metals, because the primordial gas should not be very metal rich, but we're using metals to trace it. So we very likely are going to get some feedback that creates this carbon-4 and O6, and that is going to be injecting these. So absolutely, that must be happening at some level. You do have to put the metals up there. We're not at the point yet to do like element by element abundances, but that's certainly something that we'd like to do and should keep looking at.
I think we need to move on. Let's thank Andy again. And next we have Claire Murray from also Space Telescope Science Institute, and she'll be speaking to us about the enigmatic ISM of the XMC.
So hello, everyone. Thank you for being here, and thank you to the organizers for the opportunity to tell you about the ISM. I've learned a lot from all of you this week about the stellar populations and the dynamics and the context in the local group of these beautiful systems. And I'm really happy for the chance to drill down and talk about the gas and dust. So I think the context for these systems needs no introduction. It's a real privilege to not have to beg and plead you to care about them, because I think we all do. But I would like to mention the two reasons why I find these systems to be most interesting. And the first is that they have very diverse interstellar conditions. I care about galaxies as baryon factories. Like, I want them to understand how these galaxies form stars from their diffuse reservoirs. And these things are very different from the Milky Way. And so we can get a good leverage on different conditions that are prevalent at different redshifts. They're also extremely nearby. So we can think about them as like in a holistic way, without having to worry about the effects of being embedded inside of them like we do when we study the Milky Way. So zooming in on the two clouds, this is a gorgeous optical view of the systems, and I completely forgot to put the credit to the amazing photographer who made these images. I will put it in the Slack later because he's amazing. But what you can see here are the conspicuous features of the clouds, including their bars, their arms, the wing, but you can also see a hint of their interstellar medium. In fact, the most beautiful aspect of these images is the pink emission, which is coming from ionized hydrogen in the Magellan clouds. If we were to tune our eyes outside of the optical into the infrared and radio, this is what our view of the clouds looks like. And when we look at them in this way, which is from maps that Chris Clark is going to tell you much more about later today, we instead focus on where we see high density peaks and low density peaks. Especially in the LMC, you can see that there are these bubbles and voids, which are due to feedback from massive stars and supernovae blowing out cavities in the interstellar medium. In the SMC, the picture is a little bit more complex, but of course we'll get to that later. But I said that these things have different interstellar conditions. And so what do I mean by that? What can data like this actually teach us about what the ISM is like in the MCs. And so first, I'd like to highlight this recent paper by Annalisa that we heard about earlier in the week, which is a tour de force of characterizing the neutral gas phase metallicities. And we can see that the metallicities are very different in the clouds versus the Milky Way, especially the SMC. If we look at dust extinction, and here I'm showing extinction as a function of wavelength for the Milky Way, LMC, and SMC on average. And you can see that dust extinguishes light very differently in these systems than it does locally. And this has huge implications for how we calibrate our observations, but it also tells a really compelling story for what dust grains are like and how they behave in these galaxies. In addition, we can look at the ratio between dust and hydrogen, and we see that it varies a lot between these systems and between other local group galaxies. Again, something that Chris is going to tell you about later, but is also super, super fascinating. We can look at the mass budget of the ISM in the Magellanic Clouds, and compare them to the Milky Way. For example, a very sort of back of the envelope rough approximation for how mass is organized in the ISM locally is that it's mostly neutral, and then the rest is about 50-50 molecular and ionized. But when we look at the MCs, it's a totally different picture. The LMC and SMC are mostly ionized and have a lot of neutral gas and a very small fraction of molecular gas. This is a slide I put together this week, and I had never thought about it this way before. Of course, these fractions have large error bars. They rely a lot on the geometries of the systems and the tracers you use. But I think even with those uncertainties in mind, I think it's still clear that these systems have very different makeup of their interstellar medium. Zooming in to just the neutral hydrogen, we've seen a view of this data set several times before, but this is a zoom in onto the LMC and SMC themselves from the Parks data set shown in those lovely colors by Andy earlier. And what we can do with this H1 is we can actually look at the temperature of the gas and see how it varies between the systems. In the Milky Way, we know that the ISM is mostly warm and about 30% cold. And when I say cold, I mean about 100 degrees, and warm, I mean about thousands of degrees. But when we look in the XMC, we see that the gas is much toastier. We have a much smaller fraction of cold neutral medium in these systems than in the Milky Way. And so understanding this and why this arises is one of our main goals, of course. It's what keeps us in a job. And the main thing that we take advantage of here is we take advantage of the extreme proximity of these systems. The LMC and SMC are very nearby. We've talked about this a lot. The canonical distances are about 50 to 60 kiloparsecs for the two systems. And so because they're so close, we can resolve individual ISM structures as well as the individual sources that are forming from these clouds and feeding back into them. And I think as an employee of the Space Telescope Science Institute, I would be remiss if I didn't show you any JWST data. And so this is, of course, a JWST mosaic of the 30 Doradus region. You can see the beautiful star cluster and the beautiful dust structures into which it is blowing bubbles. I also particularly love this ERO image of NGC 346, which is the biggest or most active star forming region in the SMC, where you can see these lovely filamentary structures. And so resolving these structures is really important for understanding, the star formation process in detail, the efficiency of the galaxies at forming these types of molecular gas. But it's actually very hard. I mean, if you have a telescope like JWST, it looks really easy, right? You can make these beautiful maps and you're done, right? But if you're looking from a holistic view of the wide scales, resolving these structures is very tricky because they're very, very small. So for example, this is a wide area view of the SMC from a recent paper by Nick Pingle as part of the GasCap collaboration. And I've just highlighted a region in the north of the SMC where ALMA did a director's discretionary survey. So zooming in on that region, we see that the H1 is organized into large structures. Our angular resolution is pretty poor. But then when we look at what we see in the CO, it looks like this. So the densest molecular structures in the Small Magellanic Cloud are not even being resolved by these observations. They exist on sub-parsec scales. They are tiny. It's like somebody took a clump of dust and just went, it's like a snow field on this thing. And how they correspond to the different H1 structures is an open puzzle. We're still working on getting even higher resolution to fully resolve these things. And so in this talk, I sort of have taken a little bit of a liberty to focus in on the SMC in particular. I think the LMC gets a lot of love because it's the bigger one and it has a lot to do with the dynamics and it's rotating and how nice. But the SMC is actually a particularly special environment, not only because of the stunning, interstellar medium views, this one from the Herschel Heritage Survey. My favorite fact about the SMC, which I mentioned in a discussion yesterday, is it's really bad at forming molecular gas. When we look at the H1 content, we see there's a ton of atomic gas. And then when we estimate what the molecular gas population is, this not based on CO, just based on our estimates of the total column, we see that it just has basically no molecular gas. So why is that? Why do we see active star formation, but basically no molecular gas where we have rich atomic reservoirs? The punchline, which I'm sure you all know I'm going to get to, is that there are many open questions about its line of sight geometry. We actually don't have a good handle on where this interstellar medium gas is living along the line of sight. And that is really important for understanding why it's so bad at forming molecules. And so I thought I would start with an overview of what we know about the SMC structure. We talked about this in a really awesome session on Monday and drew a bunch of cartoons. And so I turned those cartoons into a slide for all of you who weren't part of that session. So this is a top-down view of the XMC system. So we've got the LMC at about 50 kiloparsecs and the SMC at about 60. And we're observing direction is from the bottom. And so old stars are pretty much spherically distributed in the system. Makes sense. When we look at Cepheids and our Lyrae, we see an extended distribution along the line of sight. So if this is our observing direction, we're basically looking at a cigar end on. These sources extend by 20 to 30 kiloparsecs along the line of sight, which is quite amazing. If we look at other tracers for which we can measure distances, we see that the Eastern SMC is deeper than the Western SMC. And there's a bimodality in distance on the eastern side of the system. And so we have lots of pieces of evidence for what the structure of the system is, but the interstellar medium is nowhere in here. That's because it's very, very hard to measure distances to diffuse gas structures. But we know that it's not simple. So when we look at the SMC with a beautiful data set like the one from GasCap, on the left, I'm showing just a face-on view. And on the right, I'm showing a visualization of the data cube. Basically, if you take your position, velocity cube and tip it on its side and look at how the radial velocity structure, what it looks like, you'll see something like this. You've got oh my gosh, is this pointer gonna work? You've got these crazy loops and lines, and it just looks like a total disaster. And this, has long been known and has often been, explained away by the fact that we know that the SMC has interacted with the LMC a lot. It's formed fabulous structures like the bridge, the stream, and the leaning arm, which I meant to say on this slide, which we've already seen a lot. But the problem is that when you integrate up all that H1, you get a map that looks like this. And so this map is like a perfect example of what a rotating disk looks like. Like you can fit a rotation curve here, fit a dark matter profile, measure a mass, and that's what we've been doing for decades. This map is one of our best constraints for the total mass of the SMC. But as has been shown in simulations and in observations of other galaxies, a lot of kinematics can conspire to look like a simple rotation curve. And in this case, that's what's happening. It's basically like a rotation ruse. Ask me. So we went in and actually tried to test this directly. So we identified a sample of stars for which we had radial velocity measurements as well as proper motions. These are young, spectroscopically confirmed massive stars in the system. And based on the rotation model, we expect those stars to orbit around the system in something that looks like this. When we look at what the actual observed proper motions of these stars are, they look something like this, which is considerably different. You'll see evidence for tidal expansion. You see stars moving off towards the LMC and off in the other direction, and a big jumble in the middle. And so the conclusion from this is not that it's definitely not a rotating disk, but that if it is one, it's very complicated. And so I think it's definitely at least not a simple model as can be applied to the integrated field. So what is it? To investigate this more, we took a deeper look at the radial velocity structure of the gas. And so basically what we did is we took this, rotation curve map, we plopped down a bunch of points and looked at what the H1 profile looks like at each one of these positions. And I've colored these blue and red just to guide your eye to show that across most of the SMC, H1 is organized into 2 peaks or more or fewer. But in the middle of the galaxy, it mostly has 2 dominant structures. And so to analyze what these structures look like, we identified a broader sample of massive stars. These are red supergiants identified in Gaia and Apogee. And we looked at little groups of them, matched their radial velocities to the velocities of the gas, and looked at a comparison between how the extinction towards these sources varied as a function of velocity. So basically what we're doing is we're comparing the extinction towards stars in the low velocity peak with the extinction to the stars at the high velocity peak. And basically this exercise gives us a measurement of the difference in extinction between low and high velocities. We can do this across the SMC. In practice, we split up the SMC into a bunch of different bins of varying Voronoi tessellations, but that's a detail you can read about in the paper. So basically, if gas at low velocity has more extinction than gas at high velocity, then we say that the low velocity component is behind and vice versa. And so we made this measurement without any sort of prior idea of what our results would look like. And so after binning the sources and computing this statistically, we found a map that looks like this. And so remember, where it's orange, gas at low velocity is in front, and where it's purple, gas at low velocity is behind. And so we were very surprised to see like pretty coherent structure across the base of this train wreck. On the western side, we have mostly orange. On the eastern side, we have mostly purple with some deviations. But this exercise, what the sort of punchline here is, it allowed us to separate these 2 samples into front and behind massive stars in the system. I've colored them purple and green. Those colors will continue in the presentation. So some interesting things we can do is compare these to other tracers. Here we show that CO gas is mostly aligned with the front component. This is a right ascension radial velocity plot showing that CO, which is in the black contours, matches up perfectly with the profile we see in the front component. We can look at the abundances from apogee of these samples and notice that they're significantly different. We see that the highest metallicity sources are found in the front component, whereas the lowest metallicity sources are found in the behind component. And so these pieces of evidence are sort of piling up to put together a picture where these systems might be significantly different. And we can use Gaia proper motions of these 2 samples to make a simple toy model for what they are. And so here I'm showing front on the top, behind on the bottom, and the radial west and north components as a function of position across the system. And you can see some obvious trends. For example, in the west component, there's a clear signature of tidal expansion by the LMC, as well as some other sort of key differences. But basically, in summary, what we did is we made a toy model to reproduce these kinematics, and we were able to separate the 2 systems into front and behind populations. In summary, the front population is the one with all the CO. It has higher stellar metallicities, and its average distance along the line of sight is about 60 kpc. Whereas the behind component, no CO, lower stellar metallicities, and a farther distance of about 66 kiloparsecs. Okay, sure. Why does that matter? Well, it gives us a new picture that the SMC may not be just a simple single system. Note that we at no point in our paper said that it was 2 galaxies, even though that is a possibility that we can keep our minds open to. I think the jury is definitely still out on that. But this is sort of my cartoon view of what we're looking at. The thing we're super excited about is our model is fully consistent with a totally independent measurement for where the dustiest region in the SMC lives. Petya Yanchulov America Jones, who's a postdoc at Space Telescope, did an amazing analysis of the detailed CMDs in the Southwest Bar and pinned it to 62 kiloparsecs exactly, and we're bang on that estimate, which was totally satisfying. And I think it's not inconsistent with the stellar picture that I showed earlier. We see a lot of substructure in this system. And I think the reason why I'm interested in future numerical models of the system is the timescales for these different age populations and how they react to these violent collisions with the LMC are going to be really important for sort of reconciling all of this into like a global model for the whole XMC system. And another thing that's exciting and on the horizon is the Skilla survey is going to help us actually pin down distances to these structures across the XMC. So this is a survey that I've been leading for 4 to 5 years now. We're a parallel program to Ulysses. So those of you who know your mythology, Scylla is like a 6-headed monster that attacked Ulysses on his voyage. And so that's why our logo has a 6-headed monster on it, and it's not an acronym. Fun facts. And so basically, you'll hear more about this from Christina later this afternoon, but what we can do is we can constrain extinction and distance towards hundreds of thousands of resolved stars across the system and actually do detailed modeling of its 3D structure, which is going to be so exciting. In addition, in terms of exciting new data on the horizon, our view of the ISM in the XMC is about to come into extremely sharp focus. So this is, again, the Parkes gas H1 map of the XMC at 16.2 arc-minute resolution. And this is the view that we get with gas cap H1, which is at 45 arc-second resolution. And so we're going to be able to not only resolve small scale structures within the systems, but also their CGM and gas outside of the galaxies. This is just a preliminary map of where our data processing is at the moment. And so papers should be coming out this year. And so I think I was really fast because I definitely want to have questions about this. But overall, I think that the XMC ISM is complicated, but that's what makes it interesting. We can learn lots of things about the mass budget, about dwarf galaxy interactions, and the formation history of the system. And so with that, I will take questions.
Awesome talk, thank you. In your updated schematic with the gas, I saw the front part, you had little arrows. Is there evidence for a rotating disk if you isolate to look at the gas just in the front part?
Yes.
Awesome.
So it's not super clear evidence. I mean, so what we did basically is we looked at the after subtracting the systemic motion of the SMC and correcting as much as we can for other effects, given that the SMC is not simple system, we do see like some residual, proper motions that show rotation in the front system, but it's very uncertain. So that's something we're hoping to drill down onto more.
Thanks.
The way. Thank you, Maria Rosa from Potsdam. This was brilliant. One of the things that struck me recently is that the SMC has this very fast outflow, and the direction of this outflow, I don't know if you can pinpoint in which direction it goes, and how would that fit in your picture? Because it's so fast that star formation is going to stop very soon. Soon. Yeah, I just want to know what you think in that respect of the different components.
Yes, absolutely. I think so. We haven't looked in detail at the outflow properties of the SMC, but I agree with you. I think the next step is to try to connect the features that we identify in the two components. For example, this feature extending to the northeast is where we see a lot of outflowing gas from the gas cap emission data, and so trying to reconcile that with what they see in, as well as the broader scale CGM structures that Andy mentioned earlier, is something that we need to do next. So, and basically TBD.
Nice talk. Could you come back to that slide in which you try to understand the direction in which the young stellar population is moving?
The kinematics.
Yes. I was wondering, yeah, this one, that when you see the models and then you compare to the observations, it seems a mess. When you realize that perhaps we have these two, the behind and the front components, have you seen if you divide this group of sources in behind and front, it gets better? It seems better or not?
Yeah, and so we see tentative evidence for rotation in the sample from the front component, which is consistent with our super simplistic toy model. But that's something we want to do more. I mean, I think based on the results from Paul Zivic's work, where they analyzed rotation in the older stellar populations and found that there was evidence in the central regions of the galaxy, whereas in the outer regions, they're totally dominated by tides. I think that's something we didn't do here, but I'm hoping to do in the future, is actually look in a region by region basis to see if we can see it, because I think that would be cool.
Thanks, this is brilliant and surprising. I was really curious about the molecular and like the cold component. You said that you know, at the beginning that the LMC was particularly bad at forming molecules, but then if you decompose it in the two components, would your and then you show that the CO is in the front one. So would that at this point, like, is the front component more normal, like as you expect? And
yeah, I think that's totally right. We haven't done the quantification of like the molecular gas fraction yet, but yes, absolutely. Basically, the punchline here is that, you know, like, I guess the question of whether or not the SMC is one thing or two things is sort of like, well, who cares? But from my perspective, it's very important for that reason, because you want to make sure you're associating the molecular gas with the atomic gas and the dust that is actually part of the same system, so that you do a more accurate job of understanding their star formation efficiencies, their depletion times, all of this. So yeah, it's something we're going to be doing soon.
Yeah, this is really fascinating. So would you maybe give this as a point in favor of the collision model of the LMC and SMC? Unless there were two systems sort of for a long time, this closely associated, my intuition would say that a collision could produce a lump of material like this out of the larger galaxy, whereas just a regular close interaction probably would not. But
yes, absolutely. I think we have pretty good agreement, as Cortina showed this yesterday, but it's possible that the second component is associated with the so-called counterbridge. And I think the model 2 from her simulations agrees very well. Although model 1 agrees much better with the stellar stream that we saw yesterday. So I think, you know, more models are needed.
Kat Barger, Texas Christian University, to extend past this collision idea. So like, you know, how would we expect the stars to react from a collision versus like the gas? Like eventually the gas might settle back down into something normal. Do we have an idea of what kind of time scales we'd expect for the stars to behave normal versus the gas to behave normal? And would that maybe help us understand why the H1 doesn't look too bad?
Scott. I mean, yes, I think that's a good question. I think that's why we need to, this is like, basically this whole paper is my pitch to theorists to start using the SMC as a thing you care about in your simulations.
I'm on board.
Yay.
Any more questions?
Yeah, hi, very nice talk. It's about the constraint about the density distribution along the line of sight. Is there any possible way to just use a model, just like the turbulence model, to give some very very rough constraint, and then combined with the observations and give us some rough distribution. The third study.
Yeah, I mean, I think you mentioned the turbulence model. I think there's a lot going on here that we still need to reconcile. There's been a lot of turbulence studies in the SMC, and also studies of the filamentary structure of the gas has given us ideas about magnetic fields. I think the jury's still out there, but we're definitely hoping to include those constraints in our sort of future pictures of what this thing could be, especially in concert with new simulations.